Okay, everyone, thanks for joining us for the first talk of the year, which is going to be given by Jordan from Zama, and he's going to be telling us about some of their work on fully homomorphic encryption.
Thank you, Thomas. But first, if anyone has questions, I don't see the chat, so not hesitate to interrupt me. So my name is Jordan Frery. I'm working currently at Zama, where we are developing solutions around fully homomorphic encryption. Prior to that, I worked as a data scientist and did a PhD in machine learning based on fraud detection. So today I'm going to present you an open source library that we developed around the core product of Zama, which is a library that does fully homomorphic encryption. And this open source library is essentially doing machine learning on encrypted data using the homomorphic encryption. So to give a brief overview of fully homomorphic encryption, just a small disclaimer, I'm from the machine learning domain, so I'm going to give the overview here, and I'll try to answer the questions you have, but no. So currently, we live in a, let's say, untrustable world, where a client and a server have to kind of set up a trust such that the client can get some service from a third party, a server. Let's say you send something like a mail to a server and you want the server to basically do the spam detection algorithm over the mail. Since a complicated task, you often don't do this locally, so you just send the mail to the server. But you've got to send the whole clear text to the server, and the server executes the algorithm to detect whether it's spam, and it sends you back the prediction whether, or the probability of the mail to be a spam or not. So of course there is a bit of a problem here, since there is some kind of trust that is implied, because the server not only has access to your mail but also has access to the prediction, which basically gives a lot of information about the client. So what is FHE? FHE aims at providing a privacy for the user. So what happens is that, let's take the spam detection example again. You take the mail, you would encrypt the mail locally at the client machine, and you would send this encrypted data point to the server, and the server, thanks to fully homomorphic encryption, would be able to execute the same function as it would have done on the clear data and send you back the encrypted results. So of course, it applies the function over the encrypted data. The result of this function is also encrypted, and only the client, which has access to the private key, which it used to encrypt the data, can decrypt the results of the function that has been executed on the server. Right? So let's dig a bit more into FHE. Here you are represented X and Y, which can be two data that have been encrypted with a specific private key. In FHE, to maintain the security, you have some noise in what's called the ciphertext. So the encrypted X and the encrypted Y, you have some noise, which here is represented by the green level here. All right, so when you add them together, so two ciphertexts together, you increase very slightly the noise. So if you would do a very long sum, it would increase more, but this is how having operation in FHE works. So you would, having arithmetic operation between two ciphertexts would increase the the noise. But that's not too bad here for the addition. With the multiplication, same thing. If you multiply a ciphertext with a constant, the noise remains kind of stable. So what I mean by stable is that once the noise reaches this red level here, what happens is that, then the noise is basically overwriting like the actual data that's been stored in the ciphertext. So when you do a lot of computations, you will arrive to a point where the noise is quite high. So in fully homomorphic encryption, there is something called a programmable bootstrapping, which you call here PBS. At our level, at the machine learning level, this programmable bootstrapping can be seen as a simple table lookup. So essentially just mapping mapping an invariant function from an integer to another integer, right? And this is quite interesting because this table lookup allows us to have some kind of nonlinearity in the FHE circuit, but also when you apply a PBS, it decreases the noise. So you can keep working with this ciphertext that comes right after the PBS. So this is why machine learning becomes very interesting in this case, because you could have very long circuits and always play around these PBSs to decrease the noise and keep going with the computations. So let's tackle a bit more machine learning use cases here. So of course, the first one that comes to mind is based on healthcare, where machine learning is a bit stuck today because of obvious reasons of data being very sensible to share and compromises some privacy from the users. Of course, there are a lot of different applications that can be done, like face recognition, voice detection, fraud detection. Basically, any arithmetic functions that represents machine learning models can be done in FHE. So machine learning currently with the fully homomorphic encryption that we have now, we are performing the training of the machine learning model on non-encrypted data. It can be done with the open source library I'm going to present right after, but it can be done with anything you'd like, and the library is supposed to convert any machine learning model to its FHE equivalent. And the purpose of concrete ML for now is to allow the inference on encrypted data. So you could train your model, push this to concrete ML, and you would get an FHE circuit, which is with the crypto parameters to encrypt the data. So you would have to create a private key as a client. You would have to the secret key as well, and then you could deploy the FHE circuit in an untrusted server, which would run the inference of encrypted data. So we provide also in this library the fast simulation and the deployment mode. I might come back to this later. So fully homomorphic encryption, as just said, basically imply three kinds of operations. So additions, multiplications, and this programmable bootstrapping, which for us is going to be a table lookup, a very simple table lookup. And in machine learning, what you would get is matrix multiplications, which represents like more than 90% of all the operations you actually do in machine learning models. So multiplication and additions, those are pretty fine to do in homomorphic encryption. And the second part is nonlinearities. So in neural nets, for example, you want to break the linearity by adding some activation function, nonlinear activation functions. You could also have, as we will see in trees, you have some comparisons between values that breaks the linearity. And this is going to be represented using a table lookup. So overall, fully homomorphic encryption and machine learning can be matched by having two kind of main operations. So you have the ciphertext, so encrypted inputs that comes in the machine learning model that can do whatever kind of computation it needs to be done. So here the function represents the PBSs. So those could be nonlinear activation, and you want in FHE to represent them with a table lookup. The sum would be just, matrix multiplication, and then you can, thanks to the PBSs, so the functions here, you would be able to go very deep without actually destroying the ciphertext because of this noise increasing, since you can actually use the bootstrapping to decrease the noise step by step. In neural nets, these PBSs happen at every level, often at every level. So after matrix multiplications, convolutions, and things like that. Great. So now let's have a look at Concrete ML. So it's available on GitHub publicly. We are trying to release every 3 months updates. As we are working with the research teams that work on fully homomorphic encryption, we bring a lot of different improvements every 3 months. So you can check it out on GitHub. This library has been designed so that people that with absolutely no crypto knowledge could actually use it. The only thing that will be needed to know is that you have to create keys but basically training the model and deploying would be very simple here. We try to be as close as possible as what data scientists and machine learning practitioners are used to have. So in those, there is like we support Torch and TensorFlow, but also all the models, most of the models that are available in scikit-learn and ONNX. It's a representation of machine learning models using kind of graph abstraction. And it turns out that most of the machine learning framework can be converted, model can be converted to ONNX, which is the main entry point to Concrete ML. So of course we have all the popular API that you can have in Python when you work in machine learning with the feed, training a model, predict over some data, and you have some pipeline and grid search also support. Yeah. So now let's dig in how we actually change the machine learning model to make it FHE friendly. So in FHE, at least currently, we can only work with integers. So computation have to be done with integers only. And to do this, quantization, we use quantization, which is an approach that allows transforming floating points to integers. So if you take a distribution like the Gaussian distribution, you just cut the distribution over the full range. You can actually choose different quantile if you want. And you define a precision, which would be like, for example, 8 bits or 4 bits, and you cut your space into the number of available precision. A more visual example would be with pictures. every pixel in a picture is represented with 8 bits, so 256 values. If you would quantize the picture, you would see that you would lose some information along the way until you reach a single bit here, which allows to have, because there are RGB channels in picture, it allows to have some kind of a similarity. But if you would feed the right picture to a machine learning model while it has learned over the first picture, the 8 bits one, then you would get some kind of loss in the accuracy. So let's look at what's available in concrete ML and what kind of machine learning model we support here. So the first kind of model are tree-based model, so decision trees, random forest, and XGBoost, which is a gradient boosting algorithm, pretty popular in machine learning. Then we have linear models. So basically linear regression, generalized linear models, logistic regression, SVMs, and others. And finally, others that appear here, SVM, ElasticNet, Lasso Reach. And then finally, we enter the world of neural networks. We have built-in neural networks such that user can actually train their neural nets, and the neural net is going to be converted to FHE instantly. Or we can also design the neural network using Torch, TensorFlow, ONNX, if you will. And once the neural net is learned, you can basically push that to concrete ML, which will do the conversion to the FHE equivalent. So let's take a look at tree-based model here. So tree-based model have a challenge, which comes from the fact that they are built with if-else statements. So in a tree traversal with encrypted input, you would have to do comparison between for example, here, the X3, which would be encrypted, and a clear value, which would be in the clear, with this kind of thing. But comparison, doing a greater than, is not directly possible in FHE, right? So what we do is representing this comparison with a table lookup. So imagine you have X3 here, which is equal to 5. So the comparison X3 greater than 3 could be represented with a table lookup with only those zeros, 4 zeros and 4 ones. What it means is that, like, so here, X3, you would just pass the X3 as the index, and it will return whether it is actually greater than 3 or not. So this is essentially how we can do comparison in FHE now. So the second part is tree traversal. Tree traversal assume that the example is only going to go through the nodes that satisfy the condition. Well, this in FHE is not directly possible, because FHE, like in FHE, the input is encrypted. You can't really know, the server can't really know whether it has to execute the left node or the right node. So we have to execute to process every single node in the decision tree. And we do this by basically converting the tree traversal model, like inference, to only matrix multiplications and comparison, which we can do in FHE. So with an ONNX graph, it would be represented like this. A single straight graph of computations that computes every single comparison and every single condition in the tree. So this works fine for also a lot of different trees, as they are in like random forest, for example, or gradient boosting, as it basically just adds a 1 dimension to the matrix multiplications. Great.
There's a question on the previous slide.
Oh yeah, sorry.
Yeah, for these tree-based models, and I think this question applies to a lot of other models. Was there any alternative of like converting like the problem with these trees is if they're very deep, but if you're doing like random forest or something, you have shallow trees, you can sort of take advantage of parallelism. Was there an attempt to like rewrite these trees in a different form that makes them more suitable for the limitations of FHE?
Yeah, it's a good question. Like random forests, for example, they're gonna be so deep that if you don't constrain them to stop at a specific level, then they're gonna explode in terms of matrix dimensions here. So we didn't really study ways to make the random forest the entire model with only small trees, but gradient boosting, for example, is basically the inverse. You've got some shallow trees and you basically combine a lot of them, but very like not deep at all. So here it's completely fine for FHE, but you're right, random forest in their default mode would be huge matrices here. Yeah.
So I'm guessing this approach is probably taken to get all of the models into sort of the same TensorFlow graph input type of format so that they could be sort of uniformly processed, or is there like special handling for each of the different types of models?
Oh, yeah, no. So for tree-based, we actually use a library developed by Microsoft called Hummingbird, which takes any kind of tree or ensemble of trees and transform this to the matrix multiplication representation. So basically any kind of tree-based algorithm in machine learning will be represented with those nodes. Only the dimensions and the values to compare with would change. So yeah, was that the question?
Yeah, thank you.
Okay, cool. Okay, great. Okay. Yeah, so the way we use concrete ML to develop model, to train model and predict and stuff like that is very similar to what we would have, for example, with scikit-learn. So you just import a model which we chose to give the same name as they are represented in scikit-learn or in their own library. So you just define the model, and one of the most important parameter you have to give to the model when initializing is the number of bits of precision over which you want the input data to be represented. So for trees, it's less constraining than for neural nets because every single feature is going to be quantized with 8 bits of precision. So you've got, for one feature, 256 different values available, and for the second feature, 256. While for neural nets, you would have to quantize the whole input at once because, of course, you send a lot of different inputs into neurons and doing different quantization while then doing addition and multiplications on those differently quantized inputs would be very tricky to handle. So here, yeah, you can just train the model. So you define the bits, you can train the model with the fit function, then call predict, which would run basic clear inference. So you can actually test, debug the model, compute some metrics, which here would be pretty fast because it's just everything in clear. But it will give you the FHE accuracy because we make sure that the cryptographic parameters allow you to have something like 1/100,000 chance to give the wrong output. So then you can just compile the model. This compile function is going to take some representative data set and transform the model into different steps until it reaches the compiled. So we have an MLIR representation of the model, and then we can basically execute FHE pure operations following this MLIR. And yeah, of course, you can check the execution time. by just simply setting the execute in FHE here, right? Of course, X-test here is not encrypted. It's just for debugging purposes for data scientists. But then you can, once you are ready, you can just split the client and the server and then deploy, basically. So those are a few experiments of a span-based dataset where we take the floating point 32 metric. So we have the F1 metric and the average precision metric. And we compute the metrics for different, so bit width would be the n bits parameter that you just saw before. And of course, with 1 and 2, the damage done to the accuracy, so the F1 and the average precision is pretty huge, but you converge very quickly to the floating point 32 metrics, which is great. And on the bottom, you can see the inference time for a single example. So of course, here I probably would need to give you more information about what's the size of the random forest XGBoost and decision trees, but yeah.
What's the unit on time here? Knowing FHE, that could be minutes or seconds or.
Yeah, very good point. So those are seconds. Those are seconds. We basically here use the default parameter we have in ConcreteML. I think there is no depth limit for decision trees. There is a depth limit for XGBoost, and I think we set 6 of depth for random forest. So decision tree, of course, it's a single tree, so it's pretty fast. But you can see that from 1 to 6, it will triple in terms of execution time. Random forest, as you guessed, is the most costly of the tree-based model because it just builds very deep trees. And XGBoost has I guess, is more friendly to FHE because it builds very shallow trees while having good accuracy.
Did you say how big the decision tree classifier example was for like 3 seconds? Like roughly how big was the resulting network or the tree that started?
Well, yeah, so we don't set a limit on the depth. So it will very much depend on the data set. I can't really tell you. It's a very good point. I should actually write the complexity of the models here. But yeah, so it's basically trying to classify the span-based training set properly. But it's a single tree, while we have 100 here and 100 here. So yeah. Yeah. So, and there are a few visualization graph just to show that even though the decision boundaries are not set at the same place, because of course we quantize the input space, I will also basically quantize the output space in trees, well, also in neural nets. So, so you have got some different kind of decision boundaries, but the results are very similar in the end. Oh, and something I didn't mention before, but we see some kind of an effect that we didn't really expect before, like when running that, is that a quantization has some kind of a regularization effect here, right? Like the concrete has some kind of better accuracy for a moment, just because quantization makes data less precise. So yeah, great. So now linear models. So we have a few of them. We basically try to cover all the linear models that were implemented in scikit-learn. The good part here is that it is what we call leveled FHE. It's a circuit, an FHE circuit, which does not contain programmable bootstrapping. What this allows us is that we have a condition on programmable bootstrapping that I didn't say before, is that we cannot go over a certain number of bits of precision. So I can give you an example. Like a year ago, we were at around 6 bits for the input of a PBS. It couldn't go over that. We went to 7, 8 very quickly, and now we are at 16. So the accumulator cannot go to 32 bits, but we've got like 16 bits, which is quite good. But this does not apply to linear models because there is no PBS. So here you can do very large sum. We can go up to 30 bits. So for example, here the number of bits we have is a quantization on the input, but also on the weights. So you're gonna do like 12 bits, 12 bits times 12 of the bits, and then adding a bit bias. So you're gonna have some really large precision, relatively really large precision in the accumulator here. So essentially, this allows us to match the floating point 32 accuracy, but also the runtime is just super fast. We just match by an order of magnitude, of course, the floating point 32 execution time. In this visualization, we can see that while we are in the input range, the model behave quite similarly as the one on floating point 32. You can maybe see like the artifact, like the fact that basically the quantization makes the out of bound, like out of range input data just without any value. So in a FHE, it's basically going to overflow, and this is not something we want. That's why when you compile a model, you would want to give an as representative input data point as possible. And now comes the last part. So neural networks. The first thing is that we have built-in neural networks. So essentially just a neural net classifier, neural net regressor, right? And you can see it gives things like that. So as I said, one complexity with neural nets is that they do very large multi-sum. And then there is a PBS. So it's not like linear models, we can just have very large precision. We have to make the accumulator. So for every single neuron you have in a neural net, you have to make the accumulator less than 16 bits. So you can do this by either quantizing the inputs over lower bits, or you can apply different kind of regularization to make the accumulator remain around 0. There are a lot of different ways where you can also basically just break the matrix multiplication into several different matrix multiplications. But yeah, the main point is that the accumulator must not go over 16 bits to be able to use it in a PBS. So here you can see the quantization boundaries, which are much less smooth that than the floating point, of course. But the accuracy remains kind of stable. Here to train the neural net and make it like quantize it, we have kind of two different ways. The first way is training a neural network and just applying what we call post-training quantization. In this kind of quantization, you just naively take the input, quantize it, take the weights, quantize it, and that's it. You don't do anything else to your neural net. Of course, you would calibrate the activations, but once it's done, it's done. So here to have a bit more accuracy, we use quantization-aware training, where during the training of the neural net, you fake quantization. So in the inference part, you apply quantization to the weights and to the activations, also the inputs. And so the neural net sees only n bits of precision. And then you apply the gradients over the floating point 32 weights, of course. And that way you can converge to a much better solution, which make the final neural net great, with a great accuracy with only integers. The second part is one that we are actively developing. This one is developing a custom neural network. So you could take, for example, TensorFlow and create, like for example here, a fully connected model. So you can do whatever you want in the model, with the exception of a few operations that are that will be available soon, but very costly in FHE. Those are, for example, ranking or doing something like max pooling, which are costly operation. Could be done, but a bit more costly. And so the first step is, so you basically create your Keras model. Let's say it's the fully connected here. You transform it to ONNX. So there are different libraries that actually do this very easily. And then you can just send this into a concrete ML function, which is called compile ONNX model. So here we take the graph, we transform it to NumPy functions, and then we use another open source library developed by Zama, which is called Concrete NumPy, which essentially convert any NumPy functions to their homomorphic equivalent. And then you can simply, so you have a quantized module here, returned by Concrete ML, and then you can call this FHE circuit that can run over encrypted data. And of course, here from there, you can also split server client and deploy easily. So we recently developed this for a VGG-like network using quantization-aware training. So if I plot this into a graph representation using the ONNX format, you'd see that in the graph, you have some quantization node appearing that will be very useful for us, because we're going to take the parameters of this quantization and simply apply them such that now the weights and the results at every output of quant node will be integers. So in the end, what happens is that the output of the convolution can be, so must be remain less than 16 bits. And then we make the ReLU, the quant node, and the average pooling a single PBS. A single PBS for every output of the convolution, of course. But we fuse them together. And so basically, PBS takes the output of the conv, and then the output of the PBS is going into another convolution, and so on until the end of the network, where the output can be decrypted by the user. Great. So FHE guarantees privacy from a user point of view. The main thing here, I think, is to remove trust from the process of the user asking a service to a third party, because trust is not needed. The server is actually just selling a service, and the user wants the service. The user just shouldn't have to trust the server that it's not going to leak the data or whatever. Actually, even for the server, it has an advantage, because data leak happen very often, even though it's not actually the will of the company. Quantization is a heavy part of our open source library, which is a necessary step to convert machine learning model to the FHE equivalent. So we have tree-based model and linear models, which are very accurate in FHE. So of course, if you take a random forest and try to have the largest random forest, you're gonna have some trouble. But for example, XGBoost models, they perform really well with shallow trees and give some very accurate results. So, and linear models are just very, very close to their F floating point 32 equivalent. Neural network can be more constrained. These all come from the fact that the accumulator, even in quantization realm, in the research, it's very often assumed that accumulators are not quantized. So even though they quantize even with low bits inputs and weights, they just don't quantize the accumulator. So they have a 32 floating point accumulator that is freely available. Like other parts also mentioned that the input, for example, the first layer of a neural net shouldn't be quantized, so they don't quantize it, while in FHE we would like to have the whole model executed in the cloud rather than asking the user to do this. But yeah. So no worry, Concrete ML is built for data scientists. We are trying to make everything very simple and smooth, so that data scientists can do their work, their daily work, and not care about cryptographic aspect of it. So there is of course, all the scikit-learn pipeline, like the grid search to optimize the model, all available. They are supported in Concrete ML. So of course, no cryptographic knowledge required here, unless you want to check how FHE is working behind the scene. You don't need to even understand quantization, at least for built-in models. If you want to do a custom neural network model, then you'll have to know a bit more, of course. And custom models are also possible. So this is a part we are actively developing right now. So many thanks. I think this concludes my presentation. So we have the link of our repository is here. Don't hesitate to start it if you have some time. We are trying to make the documentation as clear as possible with taking into account user feedback and things like that. So you have your community link and other things that we are trying to reach the community. So thanks a lot.